Logical equivalences describe when we can replace one logical expression with another. The formal definition says that two logical expressions are logically equivalent if they have the same truth tables, same input for the same output, and we use this kind of triple barred equality sign to denote logical equivalence. So let's jump right in and do an example here with the double negation property. So what I'm going to do is I'm going to start with a single logical proposition P, and I'm going to start by negating P. So when P is true, not P is false, and when when P is false, not P is true. What I'm going to do then is I'm going to negate P one more time. So I'm going to apply a total of two negations. So if not P is false, then not P is true. And similarly, not P is false if not P is true. So the thing to notice here, the important point, is that two columns of this truth table are identical. P, the column for P, is identical to the column for not P. This means that we write P logically equivalent using this triple barred equality sign. P is logically equivalent to not P. And what this logical equivalence means is that anytime I see not P, I can replace it with P, no questions asked, and not change the truth value of the logical expression that I am working with. Here's a more complicated example. So we're going to look at one of DeMorgan's laws. So DeMorgan's laws are a more complicated logical equivalence. This time I'm going to do a truth table with two variables. I'm actually going to do two truth tables here, but I'm going to share the input variables, so that's why I've drawn two lines like this. So first I'm going to compute not P. So P is true in the first two rows, so not P will be false, and then not P will be true in the last two rows. For Q, I have true, false, so I'm going to flip that, false, true, true. And now I'm going to compute the conjunction of not P and not Q. So not P and not Q. So if both not P and not Q are false, then the conjunction is also false. In fact, if either of them are false, the conjunction is false. But if both of them are true, if not P is true and not Q is true, then not P and not Q is true. Now let's jump over to the far right, and I'm going to look at the disjunction P or Q. So P or Q is true if either of P or Q are true, and that's the case in the first three rows. Then I'm going to negate that, so all the trues become falses, and all the falses become trues. Now, what we have found here with these two quick truth tables is that the row for not P and not Q, the column, is identical to the column for not parentheses P or Q. This means we have another logical equivalence because these two expressions have the same truth table. So we can write not P and not Q is logically equivalent to not P or Q. Whenever I see one of these expressions in a logical expression, I can replace it with the other, no questions asked. There's a second DeMorgan's law that has a similar structure, which you'll practice yourself soon.